Okay, hey, how are you? And welcome to the series of the tutorial questions. I'm going to go through it today as a preparation for the quiz number two calculation questions. Now, to be clear that we're going to have a series of uh, numerical questions as a part of the quiz number two, as we did in the quiz number one. And mainly all the questions going to be from the example problem we had in every module. So I'll start first with the forging question. Let's have a look on it. And you can see that the document that we have is about the open die forging process. The first question we have is going to be for the strain value, which is going to be the len of the original height over the instantaneous height. And we explained that earlier. For the force required is going to be equal to the force equal to the YF multiplied by the area, where the F is the force in Newton or pound, A is the cross-sectional area of the part in millimeters square, and the YF is the flow stress corresponding to the strain given in the equation 19.4. We're going to go back to it. Okay, now that's strain. Okay, and that's it. We are going to start to calculate the area. So the YF actually should be calculated as well. And the YF is going to be given by this equation. The YF is equal to the K multiplied by the strain up to power N, where the N and the K are going to be property for the material we are using. So once again, if we are going to have a look for the different parameters we have here, these are the equations we have, and let's see this example first, and I'm going to take you to another example which is more detailed. But in all the cases, you don't have to go to that depth. The question you're going to have in the quiz is not going to be more than 1 or 2 steps maximum. So in this example, we have a cylindrical workpiece subjected to a cold upset forging operation. The starting piece have 75 millimeter in height. So this will be the initial height. And we do have that the diameter is 15 millimeter. It's going to be reduced in the operation to a length of 36 millimeters. So it's going to be compressed from 75 to 36. The work material has a flow curve K value of 350 megapascal, and the end value is 0.17. We assume that the coefficient of friction given to us as 0.1. So you can see that everything we put in here, we need to calculate the KF. So we have coefficient of friction, we have diameter, we have the edge value, which is the height, 0.4, and then plus 1. Also, if I get to do the other calculations like the original height and the final height, this will help me to find the value for the len or the strain. Now, let's continue with that. You can see that we need to determine the force of the process begins at the intermediates, the heights of the 62 millimeters, 49 millimeters, and the final height of the 36 millimeters. Definitely in the quiz question, you don't have to do these 3 steps. I'm only going to give you one height. So if I'm going to give you this question, but in more details and show you all the steps one by one, I will go to my PowerPoint. I use this PowerPoint for my tutorial for this subject. You can see that we have cylindrical work part now have 6.25 millimeter centimeter diameter. The height is 6.25 centimeter. That means 62.5 and 62.5. Upset forge and open die to the height of 37.5 centimeter. We have the coefficient of friction is 0.1. The work material has a curve defined by the K of 280 megapascal and the M 0.15. So we'll try to solve this question once again in the same way. The yield strength is 110 megapascal. We need to remind the instantaneous force in the operation when just at the yield point reached, where the yield strain is going to be 0.002. That's the first step. Just when we start to compress the part. Then we'll reach the height of 57.5 millimeters, and then we'll reach the final height of 37.5 millimeters. Again, Just to remind you once again that we only have one of the calculation need to be done. What do we have in this equation, or in the equation in general, that we need to use the area? The area will be changed as the height is going to be compressed. But because the volume is going to be the same, we're going to use the volume as the way to find the diameter at the new height. Because you know that the volume is equal to the surface area multiplied by the height. If we know the height, we can find the surface area. And from the surface area for a cylindrical shape, we can find the diameter. Well, I'm sure that the question that I gave you in the example is much simpler than that. So at the yield point, the strain is given as 0.002, and the YF can be calculated, which is going to be equal to the K multiplied by the mu up to power n. K is 280 and the n is 0.15, so I can definitely find the YF. Now, since the work might not quite in the plastic deformation stage yet, the mu is almost exactly equal to the engineering strain value, or the strain is going to be equal to the E, which is equal to the HO minus the H divided by the HO. We remember that this is the equation that we have for the engineering strain, the original height minus the instantaneous height divided by the original height, which is going to be a ratio that have no unit. So now from this equation, I can find what will be the value for the H. So just rearrange the equation, and we can find that the new height now is going to be equal to 62.375 millimeters. Now we calculate the stress by using the equation that the YF is equal to the K multiplied by the strain up to power 0.15. And this will give me that the value is equal to 110 megapascal. That will be the value for the flow stress required to do the compression at the initial stage. Now, we know that the YF is equal to the force divided by the A. And by rearranging this equation, the force is going to be equal to the YF multiplied by the area. You remember this equation from the slide. So again, to start to calculate the force is going to be equal to the Kf multiplied by the Yf multiplied by the A. Now the Kf, as you remember, is equal to 1 plus the 0.4 multiplied by the mu multiplied by the D divided by the H. Thick is known, H is known, and the mu is known. So I can find this value. We may consider that the D value will be changed, and we can find that by calculating the original volume, and we know what the new height is, which is this one, and we can calculate what the new H is. So since the height of the workpiece has been changed to 62.375 from 62.35, the diameter also should be changed. To determine the new diameter, we use the fact that the volume of the workpiece does not change throughout the forging process. So we calculate the original volume, and this should be equal to the final volume as well. Rearranging the equation, now we know the new height, we can find the new area. That's it. We're going to apply to the equation, find the new D, using this value, find the Kf, and we again find the value for the force required to do the initial work. Now, I know this will look like quite complicated. Let's see the next step when the height is going to be dropped down to 5.75 from 6.5 or 6.25. So we start to calculate the strain, okay, the original height divided by the new height. Then we can find the value. Now we calculate the YF. The volume is the same for the original part. We calculate the new height, the new area by knowing what the height is. And now we can find the new diameter from that. Okay, now you can see the diameter has been increased because the height has been decreased to keep the same volume. Now we calculate the Kf. We multiply the Kf by the value of the area, by the value of, the Kf multiplied by the Yf multiplied by the by the area, and this will give me the value for the force. Now it's going to be 672.7 kilonewton. Now you can see that the force has been increased, and that's mainly because the part start to have strain hardening and make it more resistant to the compression than before. Okay, now if you're going to write down the steps for the calculation as what we have here. So first you know the height. Let me actually write down on the slide. So first you know the height, you know the original height, so you start to calculate the new u. You got that. Now you use the YF equation, K multiply by the mu up to power n. You got the value for the YF. Now we go for the points to calculate the volume. The volume is going to be constant because if the cylinder is going to be at the initial diameter, initial height, is going to be compressed to a new diameter and new height. So these volumes are going to be the same because it's the same cylinder, but this has been compressed. So we find the area, the new area here, and we can use it to find the new diameter. Diameter definitely is going to be increasing. We find the new diameter, we use the equation to find the Kf. Now we know the Kf multiplied by the Yf multiplied by the area will give me the force. Okay, so these are steps 1, 2, 3, 4. That's it. Now let's do it once again with the new height. Now the new height is 3.75. So step number 1 is calculate the strain. Step number 2, calculate the flow stress with the new strain. Remember that the K value is going to be constant. That's property over the metal. Step number 3, from the volume, find the area with the new height. Now, from this area, find the diameter. Calculate the Kf. Calculate the force. And the force once again is going to be increased. Now, what we can do, let's make our calculator. Make the calculation to calculate the mu. Make a calculation to calculate the YF. Make a calculator to calculate the volume, the initial volume, volume 1, which is equal to the volume 2. Okay, then calculator to calculate the area, that's the volume. Make a calculator cell to calculate the diameter, another cell to calculate the Kf, and then the final cell to calculate the force. This will give you the sequence directly, so you can get the answer. Shouldn't be hard. I showed you that in the class last week, and again to show you that once again whenever you need in a separate tutorial. So this will be the video number 1. I will go with the next video, which is going to be about the rolling process.